going to talk about genetics and breeding and what it takes to produce a successful program. Thank you guys for joining in. Like I said, we're going to try to keep this video less than an hour. I do have a video description here on some things that I want to talk about. Let me pop that up here for me to make sure I cover all these aspects. But sometimes people reach out to me for genetic advice, and they want to send me their pedigrees and whatnot and ask me to give them some pointers. And while I certainly like doing that type of stuff, it's not really practical to do that because, can y'all hear me okay, first of all? It's not really practical to do that because to really give genetic advice, you need to know the dogs in the pedigree. And while I may know some dogs back behind a certain point, in the pedigree, I probably don't know the personal dogs that you own. And unless you can describe those traits accurately, it's not going to be very practical for me to give advice. I have to know the traits, and your assessment may be different than my assessment. So what we're going to basically look at here is practices. All right. So a lot of people talk about genetics on YouTube, think that they're going to breed dogs based on their genes. And truth is, you cannot see the dog's genes for all of their traits. You can see some of their traits in what's called a phenotype. The phenotype is what you're looking at. Phenotype means, actually, it's more than what you're looking at technically. Phenotype means the traits that are expressed. A genotype is the genes that the individual carries. So like Reptar's here by my feet, he carries one set of genes, and that would be his genotype. And then over here we've got we've got Chewy, and Chewy carries another genotype. So, but I can't see their genes. I can't see their actual genes. What I do see is some of the physical traits that are expressed, but then they also have other traits that are expressed that I may not see. For example, like their hips. You may have to get an X-ray for that, but that's still a phenotype. Their testosterone or growth hormone levels. I can't see that, but you could get a blood test on it, and that would be their phenotype. The genotype is actually going to be the code that produces the phenotype. So a different set of codes will produce different phenotypes. If you have big A, that's going to be different than BB. And if it's a co-dominant or incomplete dominance, both of those will be different than AB. But if you have complete dominance, then one gene will dominate the other. Let's say A dominates B, or big A dominates little a. Well, in that case, big A, little a would be the same as big A, because that would be dominance. All right. Yeah, that's right. So genotype is the genetic code, and phenotype is the traits that are expressed. We cannot look at an individual and determine their genotype. We can only look at an individual and see the traits that are expressed. Now, if you want to do genetic testing, then you might be able to see the genetic code, right? But not many of us are doing genetic testing. Not only that, but even if we did do genetic testing, we would have to know which gene produces what trait. And in some cases, we do know that. As a result of that, when we're isolating specific traits that are important to us, we can certainly breed for phenotype to phenotype to address, maybe increase the desired phenotype that we like. But what about if a dog has one phenotype that we like, but then it has another phenotypic trait that we don't like? And this is the real aspect of breeding, because unless you are limited and you don't understand canines very well, the truth is we breed to the dog. And what I mean by that is we got to take the good with the bad. We would love to just keep the good, but we can't just keep the good. We're also going to get the bad. So with the good traits that one dog has, they're going to be combined with the good traits that another dog has, but they're also going to be combined with the undesired traits that a dog may have. So we're not always breeding trait to trait, we're breeding dog to dog. And the reason why I say that is because people will sometimes say, I select for desirable traits. I select for desirable traits. And that's certainly true. But the truth is you're breeding to the dog. And that dog, every dog's going to have some undesired traits because perfection doesn't exist. Some people might say this is the perfect dog, but it's not. There's something in there, whether you can identify it or not, that is not desirable. There's no such thing as the perfect animal. And the reason why there's no such thing, Charles Darwin even talks about this, is the environment and the requirements are constantly changing. And so if you have a perfect genotype in one environment, you put yourself in a different environment, and all of a sudden it's not a perfect environment. And since we live in a world that has 4 seasons, the environment's always changing. So the dog that's best in the wintertime might not be the best in the summertime, etc. And so we need to acknowledge um, the limits of ourselves as man. We are not gods. We're just mankind, and we can do the best what we want to do, but we're still going to be limited. And if you really want to be successful, I suggest we check our egos, put our egos aside, learn the strengths and weaknesses of our abilities, what we're able to do, and we move on from there. So yes, it's nice to breed for genotype. For, let's say you want to fix one specific trait, then you can breed for phenotype to get a desirable genotype. If you're doing one specific trait, maybe in a couple of cases you might be able to do 2 or 3, but dogs carry many, many, many traits. It's not just one, it's not just 2, it's not just 3. So as much as we want to breed for phenotype or genotype, we're really breeding to the dog, which means we're breeding the entire genome, the entire genetic code that that individual has. And this is why performance selection is necessary. Performance selection is the best way to get a true measurement of all the genes that an individual has and then select the best combination. It's not the best trait, but it is the best combination of traits. And over time, by continually selecting for the best and the best and the best, we might have one individual that's really good because it has this, but it's not so good because it has that. But it still does, better than average because it's so high in this particular trait. And then we have another individual that might even be comparable and kind of tie it because it's like this. But over selective breeding over time, continually trying to progress, we start to slowly work up both of those traits over time in the population. And then eventually we produce individuals that have more and more desirable traits than what their ancestors may have had. And this is what genetic selection does over time. And so we're going to look at this process and how it occurs let me do a few screen shares. And before I do that, I think I had another topic that I wanted to discuss. All right, so I mentioned outcrossing, line breeding, and inbreeding. Now, most of y'all know what these particular things are. Thank you for the donation. I certainly appreciate it. Not necessary, but if you enjoy this channel and you find it informative, we certainly appreciate your support. Thank you very much. All right, so as far as outcrossing is when you're going to take 2 different breeds or 2 different bloodlines, individuals that are not super closely related. They may be related in their past, a long, long, long way, like many generations ago, or like 4th cousins, something that's so small of a relationship that basically it's the same as breeding with an unrelated individual, because any ancestor that is found in the background is so far removed that it's no longer, I knew that my screen looked a little funny, it's no longer something that is going to be a concern. Like, we're not going to have accidental arrival or expression of undesirable traits at a high frequency. All right, it may happen from time to time, but it's certainly very rare when you deal with outcrosses that these undesires are expressed, because most undesires are recessive genes, which means most undesired traits are not going to be expressed unless they're what's called homozygous. They get 2 copies of those genes. The reason most undesired traits are recessive is because if they were dominant, it would only take 1 copy and you would see it immediately, and it would cause a lower reproductive success. And since it's lower reproductive success, generally speaking, dominant undesired traits tend to be selected against very quickly, and their frequency, allelic frequency, goes down in the population, which means their genes go down in the population. So as a result of that, most undesired genes are going to be recessive. And so when you're dealing with outcrossing, it's very unlikely that you're going to have 2 individuals that are unrelated carrying the same recessive gene multiple times, or multiple copies of similar recessive genes, to the point of getting more than 1 or 2 undesireds being expressed. It can happen, but it's pretty rare when you're doing outcrossing. However, because you have what's called a high degree of heterozygosity, which means the genes are different, because of that, you might get general health, but you don't get a lot of consistency. And since you don't get a lot of consistency, let's say you have an individual that is an extremely great performer, but when you reproduce it, you don't always get extremely great performers. You have some that are performing well and some that are not so performing well. So when you get that extremely great performer, it may be desired to do a line breeding or inbreeding on that individual. And so by line breeding and inbreeding on that individual, we're going to increase the frequency of the desired traits that individual carries, and therefore increase the probability that those traits will be expressed in their progeny, their offspring. All right. And this is how over time we get more and more desired traits. So we select for A, and it becomes more and more common in the gene pool, but we find that B, maybe another trait, may be beneficial as well, and we can line breed on that and make that more desirable or more frequent in the gene pool as well. And we get multiple alleles that are being displayed at a high frequency. Now we have consistency of reproduction starting to be more common in the population. So this is the difference between breeding for genetics versus breeding for phenotype versus breeding for the genome, which is the entire genetic code or all the phenotype in the dog. So breeding for the genes versus genotype, phenotype, dog, and population. Over time, we select for the population to improve. And so outcrossing increases heterozygosity. Line breeding increases homozygosity slowly enough that we're not going to have a high likelihood of locking in detrimental traits. It can happen, but it's not as likely as with inbreeding. Inbreeding, we very quickly lock in the desired traits, but we also very quickly lock in the undesired traits. So there's a time and place for each of these. Another thing that I mentioned in my video description was dual-sire breedings. I think personally dual-sire breedings are a bad idea. There is a time and place for it, and we'll discuss that. But generally speaking, it's a bad idea. The reason why it's a bad idea is because let's say the offspring are really good or they're really bad. Well, now you don't know, who do you give credit to? Do you give, well, obviously the mother's going to have some blame or credit, depending on if it's bad or good. But which sire? Let's say you have some pups that are good and some pups that are bad. Now you don't know which sire is the one that's responsible for the good and which sire is responsible for the bad. So generally speaking, dual sire breedings are something to be avoided. Now, when might you do a dual sire breeding? Well, I'll tell you this. If you're going to do a dual sire breeding, you must DNA test the parents and you must DNA test every single pup. By identifying who's the sire, it allows me to identify which sire is responsible for the deleterious trait or the undesired trait. All right. When would I make an allowance for doing a dual sire breeding would basically only be if I absolutely wanted puppies from both sires. Okay. If I really wanted puppies from both sires from a particular female. Even then, though, why not split it? Why not do one sire on 1 year and the next sire a year later? The only exception for that would be maybe the female doesn't come in heat, but maybe once a year or once every 2 years, because there are females that don't have regular heat cycles. But then also one could say a dual sire breeding is beneficial. Let's say if you have 2 older males, and as a result of that, or maybe at least 1 older male. So there's a high chance that the female might not even get pregnant, and you don't want to waste the breeding cycle because you really did want to have a breeding done successfully. So if you're dealing with an older male or an older female, or you want puppies out of both litters and you're already getting up there in age, or the female doesn't have heat cycles on a regular basis, these are all times when it would be justifiable to do a dual sire breeding. But if all the dogs are young and the female has regular heat cycles, then there's no need at all in doing a dual sire breeding. If you're doing a dual sire breeding and the female is young and has regular heat cycles and the males are not old also, then in my opinion, you're not doing it really most beneficial. And the reason why I say that is because every population, every litter is going to have some degree of variation, which means that bell-shaped curve. And if you have a small litter, you might be missing on those exceptional individuals by splitting the litter and only getting a few out of this one and a few out of that one. So that's why I think it's not wise to do dual sire breedings except for very rare situations. All right, the rest of this video, let's go ahead and discuss some of these genetic terms so y'all can understand some of these other aspects of breeding that I think are important. I'm going to share my screen, and we're going to start off with the founder effect, because if you're going to be a breeder, then that means you are going to have to go out and get an initial population to work with, and this is your founder effect. The most important thing that you can do as a breeder is be objective, critical, and skeptic. Okay? Now, let me explain the difference between a skeptic and a cynic. A skeptic only believes something when it's proven true. You can trust but verify, so to speak. I might believe this person, but I'm going to verify it. All right? I'm going to go out and look at it and see it for myself. Trust but verify is a very good philosophy, and this is what a skeptic should do. You don't want to be a cynic. A cynic is just a person with a negative attitude. You can present them with truth and truth and truth, time and time again, proof and proof and proof, and they're still going to just believe what they want to believe. That is a bad idea. All right, these type of people will waste energy and waste time. Look, for example, what are these? They call these people these furries and these transgenders. They try to redefine terms to their own liking instead of just accepting the truth for what it is. All right, this is like a cynical mindset. So you're so biased that you're no longer open-minded to truth. It's important to be open-minded to truth, but still question it. And that's what a healthy skeptic should do. So when you're going out to get your foundation, there's a lot of people selling snake oil. All right. And since there's a lot of people selling snake oil, you need to confirm that not only is the bloodline able to really represent what it's known for, but also the breeder of that bloodline that you're going to be working with, as well as the dog and the family, those particular animals are representing the traits. So here we have a bunch of blue and red dots, right? So from this population, this is the original population. You're going to start your yard here. Okay, you have a foundation. This is the founder effect. You could select just the red ones, or you could select randomly to represent the entire population, or you could just select just the blue ones. And whatever you select is going to basically dictate the allelic frequency and the phenotype of your progeny or your productions later on. Now, maybe, let's say, for example, let's just say, for example, that red is recessive to blue in this case. Well, if red is recessive and you only select reds and you breed reds with reds, then all of your offspring are going to be red. If blue is dominant and you select blues and you breed blue to blue, you're not going to just get blue. Some of these individuals that are expressing the blue phenotype will be carrying genes for the red phenotype. And so when you breed blue to blue, sometimes you might only get blue because they were homozygous dominant on blue. But if they're heterozygous, remember, hetero means different. Just like heterosexual means the sexes are different, homosexual means the sexes are the same. So heterozygous means the zygote, which is the sperm. A zygote is the cell that's created from the sperm and the egg. The zygote in a heterozygous baby, in a heterozygous egg or fertilized egg, that means the genes were different. Well, if blue dominates red, it's going to be called heterozygous. It's got a blue code and a red code, but you're going to see blue because the blue dominates. When you breed a heterozygous to a heterozygous, you're going to get some blues, but you're going to get some red. If you breed a heterozygous to a homozygous blue, all of the offspring are going to be blue, but some of them will still carry that red gene. All right, but they just won't express it. So this is something that's going to be done with like a Punnett square if you want to go back to the genetics, and you can see that type of stuff. But very seldom are Punnett squares needed when you're breeding. And there may be a few traits that you do it for, but generally speaking, it's not done that often. All right, and then you may want a population of both. Well, in this case, maybe both work well in the environment. Here's another example of the founder effect. So you have a bunch of brown moths and some gray moths. You can get a same thing as what we did before, except here we're looking at moths instead of dots. Okay. Then we have this picture here. All right. So founder effect, the next stage you're going to see bottleneck. So what a bottleneck is let me pull up another table for bottleneck because this is kind of like an important thing. This is going to be your selection process. All right, so let me share this screen. So a bottleneck is, let's say that original population is like this right here, or this one's better in my opinion. So here you have all the original genotypes and phenotypes in this original population, but you bottlenecked, meaning you're only going to select certain traits. This new foundation is a result of a bottleneck effect. Okay, and so that's why on this picture we're basically seeing that. Okay, so we're going to see that what has happened is this is the foundation effect, the original ones, but something was caused. Okay, so we have a mosquito. So the mosquito is going to wipe out certain individuals that are subject to malaria or something like that, right? And if they're subject to malaria, then you bottleneck the genes that are able to survive malaria. And then further bottlenecking over time produces a population that has resistance to malaria. So maybe let's say the yellow ones were super sensitive to the malaria and they died really quickly. The green ones were kind of sensitive, but not super sensitive. Plus, there's a large number of them. So some of them survive, but they don't do great. The red ones, however, have resistance to malaria very heavily. And so we built a new population that's high in red genes. Next thing you know, over time, the individuals that survive many generations of testing from the environmental stresses that are applied to that population, they survive because they're resistant to it and they can take it, and eventually you build up a new population that's built off of that. And this is the initial founder effect, and then you have bottlenecking that further amplifies that founder effect. All right, next we're going to look at gene flow. All right, so gene flow is going to be like your outcross. So basically you have one population that's going to jump over to another population and transfer its genes into that new population. Now remember, gene flow happens faster than genetic drift. So imagine you have like a pond versus a river. When you have a river, the water is flowing. So when you have an individual that moves from one population to another population, that individual's genes, unless something happens there that terminates its existence, that individual's genes are going to reproduce very rapidly. It's real quick movement, because if this is a male and you have a bunch of females, it can really influence that population very rapidly. And so gene flow, like a river, can change the genes or cause a lot of movement in a population very quickly. How does gene flow happen? Well, it can be moving from one population to another. Let's see, here we have a mountain. So the red birds finally got over to the mountain, and a blue bird finally got over to the mountain. And because of that, you're going to cause changes in this population and changes in this population. So that's going to be like the boat and the airplane for human beings. You know, we used to be isolated by oceans, and that's no longer the case. Now we have flow of genes. Now, the next thing that I'm going to talk about here is natural selection. So in natural selection, I hope my video is still working. I think it is. In natural selection, I had a ding on my earpiece. So in natural selection, what happens is there's basically 4 stages. Now, in this particular AI overview, it gives you 6 stages, but there's basically 4 if you want to keep it simple. first. So you have overproduction of offspring, then genetic variation, competition for resources, and then the ones that win reproduce. That's basically what's going to happen. So you might think, well, how did that variation get there? That variation got there because you had that bell-shaped curve, that population distribution. And to have that population distribution, you obviously had to have reproduction at a high rate from the previous generation. So it's all of this it's not a step of 1, 2, 3. It's a cycle that goes around in a wheel. Okay, so here we're listing it 1, 2, 3, 4, 5, 6. What I was talking about is 1, 2, 3, 4. So you have overproduction of offspring, variation exists, competition for resources, and winners reproduce. But really, it's a wheel. This continues to go around and around. So any one of those stages could be 1, 2, 3, or 4, depending on where you started in the cycle. So we have variation, environmental pressure, reproduction, and then you're going to have population changes over time. That's going to be back to variation, right? See, the population changes because there's variation, and the selective resource or the selection that the resources are putting on that population, whether it be food resources, mate resources, territory resources, or temperature, the environmental resources, or environmental stressors, all of these things are going to have an impact. And then the last tab that I wanted to share, well, before I share that last tab, when we breed in an artificial environment like my yard, we're not leaving it up to nature. I'm in charge of what's the competitive requirements. It's no longer stressed from the temperature because I control their environment. If it's cold out, I put bedding in there. If it's hot out, I make sure there's plenty of water, or I give them plenty of shade. So I'm going to try to control some of those resources. If they have parasites, they don't have to worry about that. I'm going to deworm them and things like that. So I'm going to provide the resources, but I'm going to give those resources to the one that meet my requirements. So instead of being competition for resources, it becomes competition to serve my requirements. So in artificial, or in nature, it's overproduction of offspring, variation, competition, and winners reproduce. In nature, instead of competing for the environmental resources and environmental stressors, it's going to be what's desired by the breeder. That's the only thing that changes in artificial selection. Everything else between artificial selection and natural selection is pretty much the same. All right, and then last, let's look at this tab, genetic drift. I said this happens slower than gene flow, and that's because this is done by environmental pressure over time. Slowly and slowly and slowly over time, we can change, let's look at this picture here. We can change the population of what genes are in the population, because let's say we only reproduce these, then you get this population, and then we only reproduce these two, and you get this population. Slowly over time, here this is done by reproduction. We have to go through the entire cycle. See, when you're doing the foundation effect, you don't have to do any breedings. You could just step on somebody's yard and buy a dog. When you're doing gene flow, you still don't even have to technically do any breedings. You can go to somebody's yard that's got variation, and then, like here, select what it is that you like. But so gene flow and founder effect can happen very rapidly, because that's when you're going out to get your population and bring them to your yard. But genetic drift takes generations and generations, because genetic drift requires you to go through that complete cycle of reproduction, getting the next generation, and then selecting those from there and doing it again, and selecting the next ones from there and doing it again. And over time, you improve the consistency in the population. This is something that I had to do with the Lucky 7 and Wonder Girl blood. When I was dealing with the Lucky 7 and Wonder Girl dogs, we saw that the great dogs in that bloodline were as good as anything, but there weren't very many of them. The frequency, well, when I say there weren't very many of them, let's say it was about a third that were great, a third that were not so great, and then a third that I didn't even want anything to do with, the culls. So over time of selectively breeding those dogs and using the genetic drift model through performance selection, we're able to improve those over time and then improve the consistency. Not only do we slightly improve the performance, but we really improve the consistency of expression of the performance. And this is what genetic drift does over time. And this is why it's important to deal with a specific breeder when you're buying a dog, because what a breeder does on their yard over time improves, because that's what they're selecting for. And so nothing's going to stay on their yard unless it's expressing what they are selecting for. And, you know, a lot of times when a person gets a dog from a breeder, they may never reproduce that same thing that the original breeder did because they are selecting for different criteria. It depends on what they're breeding for. So sometimes they do breed just as well, but sometimes they don't because they're maybe outcrossing it to a different bloodline that doesn't reproduce it, or because that breeder has a different eye, a different selection criteria, and they end up going a different route with it, because genes are going to continue to change in that population. There's still variation in that population, so we have to continue to isolate it and improve it. All right, let's see. Was there any other topic in this video that I wanted to discuss? And if so, I'm going to have to do it quickly because I need to go out and walk these dogs and whatnot. Let's see what else I had in this video. So I talk about understanding how multiple components could be understood when identifying polygenic traits. So let's say, for example, that there's a particular trait that you like, but it's not a monogenic trait. It's not controlled by a simple gene or a simple phenotype. This particular phenotype is controlled by a multitude of phenotypes. For example, my body weight is not going to just be a genetic number. I'm going to have things like height, muscle mass, body fat, what kind of foods I like to eat, how high my growth hormone levels are, how long my growth hormones are at a certain level, how much calcium and phosphorus are in my bones. All of these factors, my metabolic rate, the rate at which I consume, not only eat food, but also burn it. All right. So my mitochondria might come into play. All of these things are going to impact my body weight, my desire to exercise, my mental attitude. You might think, how does the attitude affect your body weight? Well, attitude affects your energy, and energy that you express is going to impact the energy that you burn or the type of work that you do. All of these things are going to affect body weight. So if you want to select for body weight, which a lot of mastiff breeders do, next thing you know, they're distorting the phenotype to get these extremely large dogs, but they lose complete function because they weren't paying attention to how each component is important. Let's be honest. Why do people like big dogs? They think that big dogs are stronger, more powerful, right? Well, not if they're fat. If you have a 150-pound animal that's built out of muscle, and you have the exact same amount of muscle in a 200-pound dog, you actually have less strength because that muscle is doing more work carrying fat. So it takes it longer to get going and longer to stop. Yes, when it hits you, if it is going, it's going to hit you harder, but it's also less likely to hit you because it doesn't have any agility anymore. So, and plus, what's going to be the impact on health? So the same thing is true for performance traits. Let's say, for example, gameness. What aspects of traits are gameness? You'll see some bird dogs that point when they hunt. Well, the hunt, chase, catch, and kill, and eat, those are all different stages of the hunting process. Bird dogs will point and stalk. They have been exaggerated on the stalk phase. Then you have greyhounds that are exaggerated on the chase phase. They may even have the catch and kill, but they're not as durable, right? It's something else like a pit bull, right? So some animals like the fight phase, and some animals like the eat phase. So different animals can be selected for different things. And then what happens when the animal fights back, the prey that is killing it, it fights back. Now you also have to have a pain tolerance aspect to it. You have to have an ability to overcome stress, heat, endurance, and things like that. So all of these different components become factors. And some people don't understand why it's maybe beneficial to make sure that you maintain a couple of those key factors in your breeding and selection process. Some people just only look at the performance, and the performance is really the ultimate measure, right? It is the best measure. But performance selection is great when you have enough population that's all you need to use. But if the population is somewhat limited, then you might also want to do some, if the population is good, you can do performance testing, super critical, or you might want to incorporate some health testing, and you may also want to incorporate some dissection of the polygenic traits into their individual components. So all that comes into play. Anyway, I'm going to wrap it up with that. Y'all take care and have a blessed day. If you like this video, hit that like button. It costs you nothing to do it, and it really helps our channel grow. Or if you feel like it's educational, feel free to donate to the channel. We certainly appreciate that as well, and you can share it on your social media platforms. Have a blessed day.